In our last example involving antiderivatives, we're going to apply it to the concepts of distance, velocity, and acceleration that we've been talking about throughout the course. Now remember that velocity is the derivative of position. So in an antiderivative problem, you might expect velocity to be given and you have to find the position function. But in this problem, there's actually two layers. Because remember, acceleration is the derivative of velocity. In other words, acceleration is the second derivative of position, which means it's going to be very similar to the previous example. So let's see what this problem says. A particle moves in a straight line and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters per second, and its initial displacement, which is another word for position or distance, initial displacement is s of 0 equals 9 centimeters. Find the position function s of t. The reason we use the word displacement instead of distance is that distance we always think of as a positive number, like how much distance did you travel? That's always going to be a positive number. But displacement could be if I'm going to the left versus the right, I can count left as negative and right as positive. So it's kind of like where I am in this coordinate system that I define. So anyway, remembering the following facts will help us. So we have a of t is equal to v prime of t, which is equal to s double prime of t. That's how this is similar to the previous example. We're given s double prime of t, which is a of t, and we're given some information about the initial velocity and the initial displacement. Initial just means when the time t is equal to 0. You're going to see that a lot in problems. Let's now go through the calculations to answer this problem. All right, so a of t is 6t plus 4. And again, we're thinking of this as the derivative of velocity. When I take the antiderivative of a of t, I'm going to end up with v of t. I'm going to take off that prime. Antiderivative of 6t is 3t squared. So I want you to verify that. Think of the antiderivative power rule. Eventually you want to get yourself to a place where you're calculating antiderivatives of power functions pretty quickly. So you'll notice through the series of videos of this lesson, that's what I'm trying to do. And then plus the antiderivative of 4, which is 4t. And I'm going to just put a plus c because every time we take an antiderivative, at first at least, we have to put a plus c, unless we have some reason not to. It says initial velocity v of 0 is negative 6 centimeters per second. So I'll plug 0 in for t. And what I'll get when I combine the given information, again, where does this negative 6 come from? It comes from the fact that v of 0 is given as negative 6. Where does all this come from? It comes from plugging 0 in for t in the expression for v of t. Simplifying, we get negative 6 is equal to c. Cool. So now our v of t is 3t squared plus 4t minus 6. At this point, we want to remind ourselves that v of t is s prime of t, where s is the position function, which means we have to take the antiderivative of v of t to get s of t. When I do the antiderivative, I just have to write it as s of t. So taking the antiderivative of 3t squared, I will end up with t cubed. Verify that for yourself. Antiderivative of 4t will be 2t squared. Again, verify that for yourself. And then antiderivative of minus 6 will be minus 6t. And again, I'm going to put a plus c. Yes, I've already used the letter c over here, but since I already figured out what this c is, if I want to, I can reuse the letter c since we've already had this c fulfill its purpose. The initial displacement is 9 centimeters. So S of 0 is 9 centimeters. Let's plug that in. We get S of 0 is equal to 0 cubed plus 2 0 squared minus 6 times 0 plus c. And again, the given initial displacement is 9. Simplifying that all, we have 9 equals c. And so our final answer is going to be S of t is equal to t cubed plus 2t squared minus 6t plus 9. And this is the specific position function that relates to this set of initial conditions and this acceleration function.